For a circular drum, we look at a membrane of radius 1, held fixed all around its rim, starting perfectly flat, but given an initial downward velocity everywhere. Because the drum is round, we write the wave equation using polar coordinates, with r for the distance from the center and t for time. Since the drum starts flat and the initial push is the same all the way around, the vibration will not depend on the angle, only on r and t. So we look for a solution of the form u of r and t equals r of r times t of t, a product of a purely radial part and a purely time part. Substituting this into the wave equation and separating the variables splits the problem into two ordinary differential equations, one in t alone and one in r alone. The time equation is the same simple harmonic equation we always get, so its solution is a sine function of time. The radial equation, though, is not a sine or cosine equation, it is Bessel's equation of order 0. The solution to Bessel's equation of order 0 that stays finite at the center of the drum is called the Bessel function of the first kind, of order 0, written J0 of r. Now we apply the clamped edge condition that the membrane must be pinned down to 0 at radius 1. This forces J0, evaluated at each allowed frequency, to equal 0, so the allowed frequencies are exactly the zeros of the Bessel function J0, which we call lambda 1, lambda 2, lambda 3, and so on. Because the drum starts perfectly flat, the cosine part of the time solution must vanish, leaving only a sine in time for each mode, paired with its own Bessel function shape in r. To find how strongly each mode is excited, we match the initial downward velocity using a property called orthogonality of Bessel functions, which lets us pick out one coefficient at a time, the same way sine and cosine orthogonality works for straight strings. Putting this together, the full solution is an infinite sum over n of a coefficient b sub n times J0 of lambda sub n times r times sine of lambda sub n times c times t, where each term is a mode oscillating at its own Bessel frequency. To check this, notice that at r equals 1, every single term contains J0 of lambda sub n, and by construction each lambda sub n was chosen so that J0 of lambda sub n equals 0. So the whole sum is automatically 0 at the rim for all time, confirming the clamped edge condition is satisfied, exactly as required.